Hey everyone, this is Jonathan. Making another video here. This is going to go over some additional techniques you can use when you are dealing with data that is either, let's suppose, with a weak statistical signal and or very sparse. Oh, excuse me here, 1 minute. All right, so the idea was there's a question in class, like I have data sets that have lots of zeros inside them, okay? So what do I do like if I have a data set with a lot of zeros? And the idea is if your data set is very zero-filled, generally speaking, you're probably going to have a very, very, very weak statistical signal from your different columns for various reasons, right? Because if everything's zero, that doesn't really tell you very, very much. Okay, so sometimes even if your data is sparse, that's not necessarily going to give you a lot of problems, assuming the non-zero values are meaningful. Also, as a general rule, lasso tends to be very, very useful for these things. Like kind of one of the big benefits of lasso regression is it'll actually go ahead and then shrink your data set. And so lasso actually has a capacity to fit your model and fit your data set, even if you have more columns than rows. Okay, so even in some fairly extreme times, lasso regression tends to be your friend. But what we're going to do here as well is talk about something else you can do to increase the amount of signal within your data and then compress it to a smaller number of dimensions. Okay. And so that particular technique is called principal component analysis. All right, so what we're going to do here, notice here, I have the Boston data set loaded in. Let's just go ahead and then just load it in. I am going to turn it into a data frame just to make it a little easier to work with. Okay, and then give it some columns. So let's run this. Oh, sorry. All right, and then here I'll create the price column. Actually, I don't need to do that. Okay, all right, so we have X right over here, and then so Y. We'll just say this is, all right, so we have X and Y right over here. So normally linear regression, what we do, we'd go ahead, right, standardize. Okay, by the way, for the technique we're going to use, you have to have scaled data. It's a requirement, just so you know, okay? Now, the idea then, right, if we were to import linear regression, we can go ahead and fit it, things like that. All right, so principal component analysis, right, it's a technique to reduce the dimensionality of your data set, all right, and actually create new columns entirely, which represent a distilled version of your data that contains most of the variance. Okay, we'll give it kind of a quick look here. You import it over here. All right, it's from a module called decomposition. Okay, and so the PCA, right, stands for principal component analysis here. Okay, and so the basic idea here, let's just kind of go ahead, import it, take it for a quick test run, and then see how it works. So we'll do this. Okay. All right, now important here, if you take a look over here at PCA, what it does. Okay, I'll give it a minute, okay. It is part of the transformer API. Notice right over here, right? So there's fit transform, and then transform right over here like this, okay. So important detail, right? So it behaves a lot like other parts of the pre-processing module, all right? Because literally what it does, right, is it transform your data to pretty much an alternate set of columns which contain a more concentrated portion of your data set's variance in a smaller number of columns. So basically what this does, all right, we'll do this. And again, important detail, right? If you're using PCA right over here, you have to do this step right over here. Okay, so just really important here. So remember that. All right, so once you go ahead and fit this, okay, the important detail, so this was X. We'll take a look at the head. Okay, so we have these numbers, 0.41, 0.41, 0.41, 0.28, 0.48, things like that. PCA, all right, the transform version of our data set. Okay, we'll just take a look at the first 5 rows. Okay, if you look at these values over here, okay, they are not the same. Okay, so note right over here, right, here we have negative 0.41, negative 0.41, negative 0.41. Here we have something like negative 2.09, negative 1.4, all right, things like that. So just important detail to keep in mind, right, is that when you sort of call fit transform, you are literally like your data is not going to be the same. It is actually a different version of the data set. So for example, you could take the information that you have right here and then using a formula transform it back into what you see right over here. Okay, so the information contained within the data set is still the same. It's just allocated in a different and more useful way. Okay, so the big thing here, right, once you call PCA right over here and use the fit transform method, when you're done, if you call tab, all right, there's something called the explained variance ratio. So if you go ahead and type this in, okay, essentially what this tells you, the data set right over here, right, XPCA, if we take a look at the shape, okay, so there are 506 rows and then 13 columns, okay. Effectively what this means, the first column in your data set, okay, the first column, right, so this one right over here, okay, this column right over here like this, okay, this column actually contains, right, 47% of the variance within your data set. Okay, and then the second column in your data in your transformation, right, 0.11 right over here. If we take a look. Okay, this column right over here, right, this information contains, right, the additional 11%, and then over here we have 0.09. Right, you get the idea right over here like this. Okay. So the idea then, all right, whereas before maybe if your data set is maybe somewhat noisy and erratic, okay, PCA, once you go ahead and apply it, right, transforms your data so that way the first column actually contains most of the variance in your data set. The second one, right, contains the second most, the third one, the third most, and so on and so forth. And so lots of times, if you take a look at this, I'll again run this right over here. All right. Effectively what this means, if we take a look at this thing, right, at the explained variance ratio, this stands for cumulative sum. So basically, if you take the previous values here and just keep on adding them together, if you kind of want a fairly precise way to go ahead and then reduce your data set, okay, we can say, after we perform PCA, if we take columns 1, 2, 3, 4, 5, 6, 7, 8, 9 right over here, okay, our data set will contain 95% of the explained variance within the data set itself. Okay, so you take a look at this then, this is a fairly analytical way of kind of figuring cutoff points for your data set. And so again, it tends to work well if you have noisy or erratic data in various ways, and you want a way to go ahead and then distill it down to something that's going to give you more reliable signal. Okay, so that's the basic idea here. Okay, so here, right, kind of the standard, right, is to include 95% of the explained variance. So looking at this, we would say include, these first 9 columns right over here. There are a number of ways you can do this, right? Like if you wanted to, like that, we could just take the results from this, and that would sort of be the equivalent of that, sort of taking these 9 columns right over here if we wanted to go ahead and do that. Lots of times, though, there are slightly more simple or more convenient ways to do it. So if you take a look right over here, okay, useful arguments you can use right over here like this, okay, where it says n components like this. Okay, you can basically just specify how many components to go ahead and keep when you go ahead and call fit transform. So for this case, here, when you have a 0.95 like this, and the first 1, 2, 3, 4, 5, 6, 7, 8, 9, all right, so n components, you can specify it in two different ways, okay? Okay, this will basically say just keep the first 9 columns of your transformation. So if you initialize it like this, all right, and then, right, take a look over here. All right, we'll see here, right, it'll just keep the first 9 columns. Something else you can do is if you pass in a decimal like this, it'll just say keep the number of components, right, that explain the 95% of the variance within your data set. So if you run this right over here, presumably it'll actually return the same results. Okay, right, same thing, right? Just a different way of kind of explaining the same thing. Okay, but in any event, right, this would be a way, right, of just kind of being a bit more careful about reducing the dimensionality of our data set and then compressing its overall signal into a smaller number of columns, okay? So kind of what this means, like for example, if we were to go ahead and import linear regression, okay, and just kind of go ahead and then take a look at this. Okay, it's 0.70. If you remember before, the original R-squared value for this data set was about 0.74. So, right, so once we go ahead and take 95% of our explained variance from the original data set into the compressed version after the transformation from PCA, if you want to double check, this number right over here would actually be exactly 95% of the original R-squared value that we had. Okay, so but again, we do this with about 30% less columns, okay? And in some cases with PCA, it's not too uncommon. A lot of times you can actually reduce things a very, very small amount. So you might have a data set with 50 or 100 columns, and you can take it down to anywhere from about like 8 to 10 and have very, very similar performance from the original one, okay? So that's the basic idea behind it. Important detail, right? If you take a look, when we fit linear regression, right, we are fitting it on the transform version of the data set, right? So the data set that results, right, after calling the fit transform method like this right over here, okay? Another important detail, right, because PCA, right, has the fit transform method, that means we can use it as part of pipelines. So for example, if we wanted to, right, we could do this. So it is pretty easy to go ahead and take this and to put it into a pipeline and then sort of make it a bit more streamlined. I'll go ahead and do this right over here. Okay, we'll do this, PCA. We'll just say 95% of the variance. All right, and then for example here, we'll do LREG. Okay, of course you could do lasso or ridge or things like that, right? And then we'll do this, pipe. Okay, and then now the idea, oh, it's standard not. Okay, right? So now, right, if we wanted to, same thing. We could just fit the original data set right over here. And again, we wouldn't even have to have this, standardized or scaled or anything like that, right? And let's go ahead and do this.